We have two 2-meter wide paths crossing at a right angle in a lawn that's 16 by 8. So some kind of rectangle. So something like that. Any questions on your picture? Okay. And it says what is the area of each piece of the lawn. So let me get this labeled at 16 meters by 8 meters. And so we want like maybe the area of just this piece. Okay, how do we do that? I probably would redraw just one little piece kind of zoomed out. And now if we have the dimensions, we're fine. So what are the dimensions going vertically for this little piece? Going vertically, like this way? What are the dimensions? It's 3, right? Because this whole length is 8, but we take out 2. But that 2 has to be kind of, so that leaves 6. That 2 has to be split between the 2. So it's going to be 3. And then how about this direction? Yep, so we take off the 2, off the 16, and we get 14 that's split evenly between those 2. So each is 7. Okay, so that's kind of a quick calculation of 21 meters squared. Okay. Picture was worth a lot in that one, I think. All right, any questions on that? How'd you do? Anybody get it? Raise your hand if you got it. If you got 21. The front row. That makes sense. Okay. Well, like I said, only 4 of you did the yard fertilizer thing. So the others of you, it would be good practice just using common tools around you, like Google Earth or Google Maps. You could do it with that. Using a scale on a map is a really good skill to have, because you can't probably Google your backyard's dimensions. Did anybody try that? Just curious. Or AI? Okay. I wouldn't do it that way. But anyway, like these kind of things come up as just being a homeowner, being a resident in a place that you're responsible for taking care of. And I feel like as accelerated math students, you should be able to do this on your own rather than have to ask somebody, right? Like pay somebody who's not as smart as you to do a job that you can do. That's something to keep in mind. Okay, yesterday we talked a lot about just reviewing all these formulas. So triangle, rectangle, those were pretty common. Parallelogram was a little bit new, maybe. Trapezoid, I think we put that on the unit 6, all those quadrilaterals, pretty sure that was on that paper. So that was review, but polygon was not. So remember we learned this new word, apothem, which is the center to the perpendicular to the edge of a polygon. And then our area for that was just a half times the apothem times the perimeter. Guys, I want you to think about where that comes from real quick. If we do like Kenzie suggested and make that a triangle, what would be the area of this triangle? What would be the equation for the area of the triangle? Go ahead. 1/2 A, the apothem, times the side length, right? If we just temporarily call that the side length. Okay, now if we just did that on every one of these, do you see how it's always going to be A, and then if we add up all the side lengths, that's P. Okay, so it's just 1/2 the apothem times the perimeter, because it's all just adding those triangles together. Okay, we just finished circles, so that stuff should be fairly fresh still. And then we talked about optimization slightly. And for our class, we just need to keep in mind that long stretched out things don't have the same area as something that's like more condensed, where the dimensions are closer together, is the best way to say that. So these two dimensions are really far apart, 14 and 1 versus 7.5, 7.5, or like 8 and 7 for whole numbers. And so they had way bigger area given a certain perimeter, which I think is just cool. All right. So this unit, again, is 3D geometry. And today we'll get into volumes, well, surface areas. We'll start there. But let me ask you first what you remember about surface area. You remember the name of that weird looking shape that I drew below the cylinder? Or let's say it's a rectangular prism. So maybe some kind of like, you just got an Amazon box from Black Friday. And if we kind of fold that out, you guys remember what that's called? It doesn't seem like the name that it should be, in my opinion. But it's a 3-letter word. Skin. That was 4 letters, but yeah. It's called a net. Does that ring a bell at all? Net. Yeah, think about folding this front face down. It would be this dimension. The back face would be this one, and the 2 sides would be that one. Okay. Of course, if we were actually going to fold this whole thing up into a box, I would have to have another. So like this would be the bottom, side, top, and then I could fold it up and then over, right? So surface area, at least for prisms, it's basically thinking through that process. Like, what does it take to cover each face? Okay? Same with the cylinder. If this cylinder has ends, like a soup can, you have actually a rectangle that makes the sides of it. We call that the lateral surface area. And then you have 2 circles that make the end. So if we folded this up, if I took this and wrapped it around, this rectangle and wrapped it around, it would make the cylinder part, and then these would fold down on the tops and bottom, okay? So any surface area with the prism or cylinder, you can think of as just putting pieces together, and each of those pieces we can find the area of, okay? Questions on that? So you can see that the second section of this unit is prisms and cylinders. I suppose we should probably define each of those things, as well as surface area in general, now that we have this review of some formulas. Do you guys feel good to move on with area? I guess I should have asked you that a little bit ago. Give me a fist of 5 with just finding area of shapes. Okay. All right, well, that was like 4s and 5s. I think we're good. So we're going to call this now surface area. How would you define surface area? Okay. Well, we'll kind of go conceptual here a little bit. So we're going to say the total area, underline that, because we will be adding stuff together for this, of all faces, which are the surfaces. That's why we call it that. Now we have to talk 3D. So of a three-dimensional, maybe I'll write that down for this time. In other words, it's not like I'm going to say what's the surface area of a triangle. Because a triangle, we would just say area. It's just one shape. But now we're talking 3D. So a three-dimensional object has multiple faces in general. We'll talk in the next section about things that don't really have faces, like cones. Or I think the next section after that we'll talk spheres. They don't really have faces, but we still will need to do area of that. Okay, so what is a prism then? Okay. Specifically, these are going to be polygonal faces. So we could have a triangular prism, a rectangular prism. Maybe we have a pentagonal prism. And it's named for the base polygon. Now, does base mean it has to sit on the ground or on the bottom? Not necessarily, okay? So let's define base. So the bases are parallel faces. It's kind of rhyming. So think now we're not talking about parallel lines, but parallel planes, which is kind of cool, right? Don't draw this, but here's what I mean. So that's supposed to be dotted. What do you see how the bottom is what shape on this? Maybe I'll add that in. What shape is the bottom of that prism? The one it's sitting on, I mean. It's a rectangle, but this is a triangular prism because the two triangular faces are parallel. They're our bases. Okay? So somewhat different. Doesn't have to sit that way. Any questions on that? Okay, then what's a cylinder? A long circle. It kind of brings up a little deeper question, like this. Can I say it's just a bunch of circles stacked? Does a circle have thickness? No, it doesn't. Technically, it's just two-dimensional, right? So, but I'm glad you brought that up. Okay. It's kind of like the infinite-sided prism, isn't it? Remember we said a circle is like an infinitely sided polygon? So this doesn't have faces, so to speak. You could think of it as a prism with circular faces. I'll write that. Sort of a prism with circular faces, or bases rather. This time I do want you to draw that net shape. So let's draw our best cylinder. It always looks like a division sign to me. So the lateral, which means side, area is a rectangle. Okay. Does it have to have the does it actually have to have area on the circular bases for it to still be a cylinder? Okay. Do we have to have these two circular bases actually have matter there to be a cylinder? No. What would it be called if it doesn't? Like a pipe, right? There's nothing on the ends, but it's still a cylinder. Okay, or like a culvert, that kind of like a drainage culvert. Okay, so it's still a cylinder even if the bases aren't present. Like think of taking the lids off of a soup can. The side of it, the lateral part, would still be a cylinder. Okay, so we've defined those things. Anybody happen to know the equations or formulas for them? Okay. Well, let's do that then. I bet you could come up with it. I think I might let you try with the cylinder. But a prism, let's say I wanted you to find the surface area of this block of wood. What is it made of? Six faces, right? It's 3 different varieties of face. So like this big rectangle, the skinny end rectangle, and then the side rectangle, the longer side. So how would you find the surface area of that? Do what? Yeah, you just find the area of each side and then add them up, right? In this case, find the area of 3 unique sides and then double them if you want to make it a little faster. Can you see if I stand right here? Okay. All right, so for a prism, we kind of defined them. Let me go right in the surface area. I should have scooted that stuff down. I think I will. Can we agree to abbreviate surface area as SA? So we don't have to write it a bunch. So there's not really a specific formula for this. It's more of a procedure. Here's our steps. Find the area of each unique Face? What does unique mean? Not the same as the others, okay? So find the area of each unique face and then add up all areas. Now, what if we have a box with no lid? How many faces does that have? 5 instead of 6, right? What if it's a triangular prism like I drew a second ago? How many faces does it have? Something like that. Okay, it would have 2 triangles and then 3 rectangles, so 5, right? Maybe it's open on one end, then it would have 4. So that's why, let's maybe clarify this. Just to remind you, like, that are present. By the way, going into Christmas, how many of you wrap presents? Okay, that's surface area, right? Most of the time we wrap the entire thing. I guess I can't really think of a example where we don't. Okay, what if we have something like this? Don't draw this, but what if we're hired to paint a barn? So maybe it looks something like this. How would you figure out, and it goes back, you know, like back here, something like that. How would you find the area of a shape like that? The surface area. So when we paint surface area. Okay, like that. So 2 rectangular prisms minus the bottom and top of each one, because we wouldn't paint that. So just the lateral surface area of each rectangular prism. And then on the triangular prism, we would do the top 2 rectangles, but not the bottom, and then 2 triangles. Okay? So sometimes it requires you to think a little bit deeper about, like, what is there? What am I actually going to be counting in the surface area? So I don't want you to memorize formulas, that's why I put that, but also don't just make assumptions. If you're ever unclear, ask, like, well, are we counting this part or not? Okay? All right. For a cylinder, actually, let's save that just for a moment. I kind of want you to be able to find your own there. Okay, do you guys want the word lateral in your, I think I put side. Is that good enough, or do you want to actually define the word lateral? Do you feel okay about that? Okay. Lateral is a word used, by the way, in medicine as well. Okay. Chicken wire or something. You guys ever use that? It's kind of a pain. All right, answer this for me. If I take a stack of index cards and squish them to the side, how is that? They call it an oblique prism. How is the volume of that related to the volume of the regular stack? Should it change? Let's say that's made of 100 note cards. Should the volume change at all? Just because we squish it and make it crooked? Shouldn't, right? But now we're working, like, this is volume, not surface area. Does it change the surface area? So it doesn't change the volume, it's the same amount of cards. Does it change the surface area? Yeah, it does, right? Think about it. Does painting this length, is it the same as painting that length? No, because that diagonal would be longer, right? Think about it like this. That's the hypotenuse, which is always longer than one of the legs. So there would be more surface area to paint if we squish it out, but the volume would not change. So that's called Cavalieri's principle. It doesn't, so you can read it, I'll help you read it. Two 3D figures have the same height and same cross-sectional area at every level, then they have the same volume. So if we even compare a rectangular prism, triangular prism, and a cylinder, as long as their height is always the same and the area of their cross-section, meaning if we slice through, if that area is the same, then the volume's the same. Okay? So that makes sense. I want to come back to volumes in a second. So let's do this one. Do you want either of these as an example in your notes, or do you want to just give it a shot? Example. Okay. I'll copy and paste this in there, but do your best to draw it. So this will be, we'll start with surface area, and then we'll add volume. All right, well, find the area of each unique face. Here's my suggestion. I definitely think it's helpful to draw them. So, area of each unique face. Let's say each one. It kind of helps you keep organized that way. Okay, so here's what that looks like. When I see this prism, I see a triangular face, and it has a height of 4 and a base of 6. Okay, so the area for that is 1/2 base times height, which is 12. Okay, what other faces do you see on here? Unique face. What other shape? Yeah, I see a rectangular shape. So you can decide how you want to orient, if it's up or down or left or right. So that's 7/5. Okay, so the area of that is just length times width, which is 5 times 7, or 35 meters squared. Okay, step 2, add up. Add all areas. And you can make life a little bit easier on yourself sometimes if you multiply by if you have repeated versions of the same face. So the total is 2 triangles plus 3 rectangles. So 2 times 12 plus 3 times 35. So 24 plus 105 is 129 meters squared. Uh-huh.
Would the bottom triangle be different from the side or the rectangle? Because it's 6.
Is it? Yeah, this one is not equilateral. Thank you. Let's back off on that. Good catch. By the way, when I draw these, I'd like to draw them relative scale. So this one should be a little bit bigger than the other rectangle. And it helps you keep track that way. Okay, same thing. I'm not going to rewrite length times width. So this is 6 times 7, or 42. And let's go over here now. So total. 2 triangles plus 2 of the littler rectangles plus 1 bigger rectangle. You don't have to draw the little pictures if you don't want. You can just add them up. All right, so 24 plus 70 is 94. Plus 42 is 136, I believe. Okay. Seem okay? Does this feel familiar? I feel like you guys do this in middle school. You used to. Okay. All right. How about this one? Let's don't do the whole problem, but what are the dimensions of the unique faces? Like this one. What should I label it? 6 by 3. Okay, what else is there? 9 by 3. And okay. All right, anyway. And then we have 2 of these, we have 2 of these, and we have 2 of those. Okay? You just multiply everything together and add them up. Go ahead and give this one a shot right there, please. Surface area. All right, let's go ahead and check in. Here are your faces. You have two of these 3x5 ones on the side. You have two 3x6, or one 3x6, excuse me, in the front. One on the back that's 3x12, and then the two trapezoidal faces, which are the bases. They're the parallel faces. And so remember that one is half the height times the sum of the bases, or we wrote it as the height times the sum of the bases divided by 2, either one. Okay, there's two of those, two of the first one. So I just wrote it out as an equation to get 156 square inches. How'd that go for you? Okay. What would the faces look like on this one? Why don't you draw them? I don't know that we'll do the whole problem, but just draw the 3 unique faces. With the dimensions, please. Zeke, can you bump himself? Can you take your hat off? Let's get to work on this. Okay, here's what you should have drawn. You have, I didn't write this, but you have 4 of the parallelogram faces. You have 4 of them. And then you have a square on the top and bottom. So times 2 of those. Does the 2.5 get used for any areas? No, remember for parallelograms, it's the height, which is perpendicular. So it's this 2, not the diagonal length. Okay? On the right side? No, because this is still a height of 2 as well. This 2.5 is this diagonal right here. Do you see it? Okay. In other words, the shape doesn't like go up where it's higher on that side, if that makes sense. The height, like this, if you want to say like the thickness all the way around is always just 2. Yeah, good thought though. Anyway, how do you find the area? We know the square, it's just length times width, but how do we find the area of the parallelogram? Did you memorize that? What is it? Okay, look it up, Put your eyes on it. Yep, it's just base, which in this case, we have this word base flying around a lot here. Because we have bases of our 3D figures, but we have also base side lengths of some of these, like triangles and parallelograms. Okay. All right, how do you feel about surface area for prisms? Okay. All right. For a cylinder, I don't think that's next. Yeah. Okay. Let me have you try this. I hope this goes well for you. And just on some scratch paper if you want. Just draw some random cylinder. And we're gonna say that it has a radius. So radius is 5 inches. Okay? Or maybe we know the diameter actually, because diameters would be easier to measure. So sorry about that, but let's change that now to a diameter of 5 inches. Okay? Give me something in life, some cylindrical object in life that would have a roughly 5 inch diameter.
A very big can.
Okay, a big can, like what?
Like those stew cans.
Yeah, okay, a stew can, sure. Maybe the oatmeal cylinders are about 5 inches. Like the kind you have to cook, not just instant ones, right? Huh? A pipe? 5 inch diameter pipe would be pretty big. But if you looked under your house, if you can do that, you could probably see a 5 inch diameter sewer pipe, like the one where all the pipes come into. That's about the size of those main sewer pipes for a house, roughly. Anyway, so that's what we're dealing with here. Okay. Now don't focus just on the 5. And I want you to keep in mind that our net looked like this for a cylinder with lids on the end, if you want to call them that. See if you can come up with an expression, an equation, like a formula for the surface area of a cylinder using the diameter only. Diameter and radius only. Okay? So account for all 3 pieces, and I will tell you that it helps if you do this. So take a sheet of paper and form it into a cylinder. It's obviously a rectangle, but when we hook the ends together in a way that it's round, it makes it a cylinder. So you don't have, a rectangle has, before we wrote length times width of a rectangle to find the area. But for cylinders, we don't have length times width. We know the height, and we know either a radius or diameter. That's all. Okay? Nothing's going to tell you. Like, think of it this way. If I have this, let's call it a jar sitting here, I could measure the height, but I could measure the diameter, but I could not measure the length of it. Not really. I mean, I could, but it would not be as easy as just sticking a tape measure on the height and the diameter. So, see if you can come up with the formula for area, total surface area of a cylinder using the diameter and radius and the height. I should have said that as well. I'll put that on here. Okay, so on your picture, this is the height. So I want you to use diameter / radius and height. Okay. Give you a minute on that. I want an expression again, an equation or... Okay, what is the area of each of these 2 circular ends? I shouldn't have probably told you the 5. That seems to have confused some of you. So just in general terms, how do we find the area of the two circular ends? Okay, so they are circles, so it's pi r squared and pi r squared. Okay? If we know the diameter, the radius is easy. How do we get it? Just divide by 2. Okay, so now we know that this formula is going to have 2 of those. If there are 2 circular ends, it will have 2 pi r squareds as the 2 circles. Okay, but now we also need to add this rectangular middle. So this dimension we know is called what? That's the height of the rectangle, or of the cylinder, excuse me. Okay? But what about the left and right, what we could call maybe the length of this cylinder? What is it? In terms of diameter, something we can measure. Yeah, that's the circumference, right? What's the formula for the circumference of the circle? It's pi times diameter, right? So pi times diameter. So the area of this part is pi times diameter, that's the length, times height, which is the width. So length times width just looks a little different here because it's in circle terms instead of length and width terms. Okay, so pi dh. 2 circles, 2 pi r squared, plus the lateral surface area, which is just an unfurled rectangle. So pi times diameter is the circumference, which is the length of the rectangle. Okay, and then the height is the width. Let's go add that to your note. Did everybody see where that came from? Like, do you kind of get it? It's easy. Once you kind of see it, it's easy to sort of be like, oh, hey, I get where it comes from now. So surface area for a cylinder is 2 pi r squared plus pi dh. And let's just be clear, this is the 2 circular the 2 circular ends, and then this is the lateral rectangle, which is circumference times height. Okay, that one's probably worth boxing. So what if you are asked to find maybe you have to go paint a pipe. And you're like, why would I paint a pipe? It's underground. Have you ever seen like culverts, ones that pass water through so that it doesn't damage things? Does anybody ever go to Moab? There's a cool hike down past Corona Arch. We've always called it Culvert Canyon, and it's this gigantic culvert that you walk through. Probably 6.5 feet in diameter, and yet you walk through. It's cool. I don't know if there's a picture of it, but. So what would you do if you had to paint the lateral surface of a big pipe like that? In terms of surface area, how would you modify this? Yeah, if it's just a pipe, you don't have ends anymore, right? So you take that off. What if it's a bucket? Just take off one end if it doesn't have a lid, right? Like one of those Homer buckets from Home Depot. You can buy lids, but a lot of times you just have the bucket with no lid. Okay? So it has a base but not a top. So we would modify that to just say pi r squared, just 1, plus pi dh. Okay. Of course, we're always going to have the pi dh. We wouldn't have a cylinder if we didn't have that part, so you won't ever take that part off. How you doing on this? Does it seem okay? Okay. Do you want an example in notes for this, or do you feel okay with it? I feel like it's just a formula. Okay. All right, if we go back to this one, actually, I'm just going to write one. Here's how a problem might sound. So a cylindrical, am I in your way? Let's do water bottle. Needs new paint. The radius is 2 inches and height is 10 inches. How much paint? Okay. Let's hold to like a minute and a half or so. My water bottles do. Otherwise the water comes out. However, if you look at the water bottles in the room, what do you notice? Hmm?
They're like, the lids are flat.
Okay. But they are also not what? No.
I don't know.
Well, we're going to model it as one. Look back at hers. What do you notice about the lid?
It's like,
Okay, but it's also not painted, right? So the sides, the metal is painted. The plastic top is dyed. It's not painted. So, same with hers. Yours isn't really the same. It's not, yeah. Because it doesn't really have paint.
just really.
All right. The lid is not painted. So we can modify this to just pi r squared, because the bottom is, plus pi dh. So pi times 2 squared. What's the diameter? 4. Okay. So 4 pi plus 40 pi. What's 44 times 3.14? Forty-four times 3.14. Okay. Okay, so 138.2 or so square inches. Who would that matter to? Huh? Yeah, like these Owala bottles. Yours is Hydro Flask, right? Like those people who manufacture those water bottles have to pay for that paint. So Maybe they want to hold the same volume with less surface area. So think about that whole idea of long, skinny versus short and squatty. Which one has more surface area? Okay, so maybe it's cheaper to manufacture bottles in different shapes so that it doesn't take as much paint to cover them. Also, it's harder to hold a big fat water bottle than a long skinny one too, right? So there's lots of design considerations when we do this kind of stuff. All right, any questions on surface area now?